26 heads out of 20.
Okay.
I had 13.
Thank you. Okay, hang on. Yeah, just keep remembering it, then I'll ask for it here in a second once I explain why we did it. Okay. So yesterday we looked at the sampling distribution of sample means. Today we're going to look at the sampling distribution of a sample proportion. So, y'all tossed a penny 20 times. So, Justine, how many heads did you get?
11.
Stephen?
13.
13. I should have asked this by now, certainly not week one. You prefer Stephen or KJ? Doesn't matter? Okay. I heard, like, Addison called you KJ. Davis called you KJ. And you answered what I said Stephen, so I'm like, which one? Okay. Olivia, how many heads? 12. Okay, and Will? 6. Okay, now if we turn these into proportions out of 20, what would 11 out of 20 be as a decimal? 0.55.
This isn't on the notes.
No, it's not. It's an activity. Okay, what's 13 out of 20 as a decimal? 12 out of 20? 6 out of 20. Now, if you get your calculator out, can I get someone to get the average of these? What's that? 0.525? So theoretically, it should be 0.5, right? Because we flip a coin, theoretically, we should get half heads, half tails. Yep, these are all, actually, there's not one, it's not one sample, it's how many samples? 4. We did 4 samples. Yep, it's not normalized yet. So, if I had the whole class do it, even then, it would only be 10 samples. So, eventually, the dot plot, if we did enough of these, would start looking kind of normal. So that's going to be what we're looking at, how we can take these proportions, and if we know the actual population proportion, then the distributions of samples should be normal with that same mean. So this proportion, which remember yesterday I said we called this P hat. That's a statistic. So if we did a dot plot, which we didn't, there has been a partial graph of the sampling distribution of all sample proportions of size 20. So just to kind of recap from what we talked about yesterday, let's say I had y'all flip it 50 times. What do y'all expect would have happened as far as how close we were to that, how close we'd get to the actual mean? It'd be pretty close, right? So as the sample size increases, we get closer and closer to the true value. Okay, so for today, we're going to use P to stand for the population proportion, and P hat, this is on page 6, to stand for the sample proportion. P and P hat. So the sampling distribution of P hat is a distribution that would be formed by considering the value of a sample statistic for every possible different sample of a given size from a population. That's our definition. And P hat, as we just saw in the activity, it's the number of successes in the sample divided by n, which is our sample size. That's how we get P hat, the number of successes divided by the sample size.
So is n always going to be sample size?
Lowercase n, yes. Uppercase N is population. Okay, so we're going to do an activity like we did yesterday with the fish, except this time we're dealing with people. Let's say we have a population of 6 students. Alice, Ben, Charles, Denise, Edward, and Frank. A, B, C, D, E, F. So we're going to keep our population small just so we can do this activity. Ultimately, we're going to start pairing them up and find every pair. Well, I'm sorry, I don't want to have to find 1,000 pairs for a big population. We're going to keep it small. We're interested, in this case, in the proportion of females. This is what we call our parameter of interest. This is our parameter of interest. It's what we're interested in finding. Okay, so what if we just say the traditional names are, or I'll say just the tradition. The names are as they appear, I guess is what I'm trying to say. So we're not going to be dealing with a boy named Sue in this case. If the name looks like a girl's name, it is a girl's name. So if we look at our sample here, or not our sample, our population, what would be the proportion of females? How many females do I have here? 2. So 2 out of 6, which reduces to what? 1 out of 3. That's our proportion of females. So we're going to select all samples of size 2 from the population. So how many different samples are possible? For dual credit, this was on our test that we took. What's it called when I try to find groups of 2?
Oh, pairs.
Well, it's a pair, but is it a combination or a permutation?
Combination.
Combination. Order doesn't matter. So this is a combination.
Is that 2/6 equals what?
Equals 1/3.
I thought it was saying like 1/3 over 3 or something like that.
It's me trying to write on top of text that appears. So if we did this in our calculator, 6 choose 2, what would we get? What was that? 15.
That's the NCR thing, right?
That's NCR. So it's going to be our job now to list all 15 different samples. Which really won't be as bad as it sounds. So I'm going to write our names up here just so we don't forget, even though they're right there on your paper. Who do we have? We have Alice, Ben, Charles.
Yeah.
Denise, Edward. They make them sound so formal. He likes being called Eddie. Or Frank. Okay, so we need to go through here and think every possible pair that we can have. And the proportion of females in that sample. So I'll do the first one so y'all can see how we want to do it. Sure. Are you saying just do like A and B? A and C? Yeah. So first one we have Alice and Ben. There's only Alice is a female, Ben's not, so 1/2 or 0.5 is our proportion of females in that group. What would the next group be? Alice and Charles. Again, there's only one female, so 0.5 is our proportion. What about the next one? Alice and Denise. They're both females, so our proportion would be 1. It's guaranteed to happen if I go into that group and pick a female. It's guaranteed to happen. Then who would we do? Alice and Edward, just 0.5. And then who else?
Frank.
Alice and Frank. Again, 0.5. Are we done with Alice? Yes, so now let's move on to Ben. Ben and Charles would be next. What's our proportion of females in that group? 0. There's no females. Then we have Ben and Denise. 0.5. Then Ben and Edward. And Ben and Frank. And we're at Frank, which tells me I've reached the end of Ben, so I need to move on to Charles. Charles and Denise would be 0.5. Charles and Edward 0. And then Charles and Frank, again, 0. We're at Frank, so I'm done with Charles. That means I move on to Denise. Denise and Edward gives me what proportion? 5. And Denise and Frank? 5. Again, I'm at Frank. That tells me I'm done with Denise. So I go to Edward, Frank, and that would be 0. So those are our proportions. Now, I want you to take these, put all of these in L1, and do one variable stats on them. And when you get it, I want the mean and standard deviation. Okay, so what are your means? 3. If I put that as a fraction, what would that be? 1/3.
0.3.
If you did it in the calculator, you get 0.3333. 0.3 repeating. So that's 1/3. Okay, what about standard deviation? Let's do 5 decimal places. Perfect. Okay, so what do you notice then about our mean? It's the same as our population proportion. All right. So it's the same as P. And then standard deviation, well, we haven't really talked about it yet. But it's similar, it's going to be similar to yesterday's. So let's, okay, we did that. That leads us to 2 rules. So rule number 1 is that the mean of sample proportions is equal to our population proportion. The mean of sample proportions is equal to the population proportion. Rule number 2, define the standard deviation of sample proportions. We do the square root of P times 1 minus P divided by N. And these rules are exact if the population is infinite. And they're approximately correct if the population is finite. And no more than 10% is included in the sample. Yeah, borrow a pencil or a pen?
I have a pen room that I guess.
Now, on our example that we did, notice that the standard deviation isn't exactly valid because we used more than 10% of our population. So, it won't be exactly valid, but it was for illustrative purposes. A little side note, someone mentioned them earlier. You know, it's been a long semester when you get told that new bags came in for the calculators and you get excited over it. You look at your calculators that have new bags. They came in! Finally! I couldn't even wait until they came in after first period. I couldn't even wait until like the end of the day. I had to just throw the old bags away during my conference and put the new ones on. Like, wow, I need a life. Yeah.
Did you like order them?
So they, one of the other teachers found them and told Miss Stanley, the department head, about them, and they ordered them for the whole department. Yep. I feel like there's not as much looseness. Like you don't have to worry about the bag.
Yeah, there's not.
Yeah. Okay. Let's look at an example. So in the fall of 2008, there was 18,516 students enrolled at California Polytechnic State in San Luis Obispo. Only 18,000?
We can afford it.
Nah. I was just thinking A&M has over 61,000 students.
I mean, you gotta think about it. Cal Poly, like, you got 30% of Texas Christian University, which is about 72,000 on average per semester, and they're coming from California to Texas because they can afford it more than
Cal
state school in
Poly.
California.
Gotcha.
There are, I seen one of my friends, seniors that graduated with TCU, and they were talking, and the parents said that they were trying to find a place, and they were trying to put them in Cal Berkeley or Cal Poly, and they said they'd seen the price, and then just for fun, they decided to look up what the out-of-state tuition was for a Texas school. And they said that when they saw TCU's out of state, they laughed at it. And then said, all right, you're going here. I was like, that was crazy to me.
Yeah. So of these students, 8,091 are female, which is about 43.7%. So we're going to use Minitab again to simulate sampling from the population. We're going to generate 500 samples of each of the following sample sizes. N equals 10, 25, 50, and 100. And then compute the proportion of females for each sample. So the histograms display this data. Those are nice histograms. Are these histograms centered around the true proportion? 0.437. Let's try to find approximately 0.437 on the graph. on each of them. I would say it's probably about right there. Probably about right there. About right there. And right there. So what do y'all say? Do they look approximately centered around our true mean?
What is the mean again? 10?
0.437.
Yeah, it looks around there.
Yeah.
50, but yeah.
Yeah. The first one, that doesn't look too good, but I mean, for the most part, overall, they seem to be pretty close to it. We could say, yeah, they're approximately centered around it. What do we notice about the standard deviations as we increase n? What happens to our standard deviation? Decreases. So just like yesterday, as n increases, standard deviation decreases. And then what do we notice about the shape of them, approximately? They're all approximately normal. Good. So this is what happens when we have an approximately normal distribution to begin with. And our percentage, if we notice our mean back here, what's it really close to? What's it, like if you think of male, female, theoretically, what would the probability be of being male or female? 50-50, right? Is our proportion fairly close to 50-50? Compared to something like 0.07? Yeah, it's pretty close. Yes.
What was the what do you notice about the standard deviation? What increases in the deviation goes?
As n increases, standard deviation decreases. So now let's look at what happens when we're a little bit further away on the wrong direction. Now let's talk about this viral hepatitis example. The development of viral hepatitis after a blood transfusion can cause serious complications for a patient. So this article, which I'm not going to read the title of, reported that hepatitis occurs in 7% of patients who receive blood transfusions during heart surgery. We will simulate sampling from a population of blood recipients. We're going to do another simulation here. We're going to generate 500 samples, again, with sample sizes each of 10, 25, 50, and 100. So here's our histograms. What do we notice about n equals 10? I know I'm skipping over the question about the mean, but let's go straight to shape for a second, and then we'll come back to mean. What do we notice about the shape of this n equals 10?
Oh, it's skewed right.
Skewed right. That's right. What about when we bump it up to n equals 25?
It's still like skewed right, but it's a little more like symmetric.
Yeah, we're getting there. We're moving the top part over. Then we get up to n equals 50.
time becomes normal.
Yeah, we're getting
Getting there.
Now at n equals 100. Now we're talking. I had a little bit of a tell, but compared to how we started, we're looking more normal, right? So on these histograms, as n increases, the shape starts to become approximately normal. But like I said, I know I skipped the question about mean. We'll come back to that in a second. And the reason this happens is, what was our probability of success in the problem? If you want to call getting hepatitis success, what was our probability of success here? According to the problem.
According to the problem,
7%. That's right, so 0.07. That's pretty far from 50%, isn't it? Compared to the 0.43 that we have. So that's why it took us longer to get normal. We're further away from 0.5. Okay, now let's actually go back and talk about the means. So first ask, is the histogram centered around the true proportion? So are we centered around 0.7? 0.7 is about there.
.7,
Or sorry, not 0.7, 0.07. Remember, our mean is our average is our balance point. So if I try to balance that graph at 0.07, does it look like the graph would approximately balance? Yeah, it does. So we're approximately centered around 0.07, regardless of what sample size we use. Then we said as shape increases, we become more and more, sorry, as n increases, we become more and more normal. This leads us to some more properties.
Mr. Schultz.
Yes.
So it's like, sorry, but like, so if it's closer to the, like if it says it's 50-50, and it's closer to that area, like what were you trying to say about that, how like the difference was between the two graphs?
So on that, what I was trying to say is if it's closer to the 50-50 split, it doesn't take as many, it doesn't take as big of a sample size to look normal.
Okay.
So if you look at our Cal Poly example, we are normal almost from the beginning.
Yeah.
But here, it took us getting all the way to n equals 50 or 100 to really start looking normal.
Okay, I got you.
That make sense?
Yes, sir.
And that's actually what Rule 3 that we're about to talk about mentions. So Rule 3 says that when n is large and p is not too close to 0 or 1, the sample distribution of p hat is approximately normal. And we saw that. When p hat got close to, when p got close to 0, it took us a long time to get normal. We got there, it just took us 100 samples. The further away say from 0.5 that P is, the larger n must be for the sampling distribution of P hat to be approximately normal. The further we are from 0.5, the larger n has to be. So when we do this, a conservative rule of thumb is if n times p, so our sample size times our population proportion, is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then a normal distribution provides a reasonable approximation to the sampling distribution. We have normal tables and we have all that good stuff. So that's information we have at our disposal. As long as we meet these two constraints, we can just do the normal table and use those properties and be done with it rather than trying to find individual distributions. So let's go back to that blood transfusion example. So P is the proportion of patients who contract hepatitis after a blood transfusion. In our case, P is 0.07. Now let's suppose that a new screening procedure is believed to reduce the incidence rate of hepatitis. Blood screened using this procedure is given to 200 recipients. Only 6 of the 200 get hepatitis. Does this result indicate that the true proportion of patients who contract hepatitis when the new screening is used is less than 7%? Essentially, if we're less than 7%, that means the treatment is more effective, right? Because less people get hepatitis. That's what we're wanting to see. Is this new treatment more effective? You gotta find out. We have to back it by the numbers.
6 out of 200.
It would be, yep. So to answer this question, we must consider the sampling distribution of P hat. So first, is the sampling distribution approximately normal? We gotta test to make sure. We can't just say, oh yeah, looks good, let's do it. We gotta test it first. So to test it, that's where we have to look at n times p. So what is our n?
Is 200.
200. So we have to make sure that n times p is greater than 10. So 200 times 0.07 will give you what? 14. Good. Is that greater than 10?
On the average?
Not yet. This is just testing to see if we can do a normal approximation.
Okay.
Now we're going to have to do n times 1 minus p. And make sure that it's greater than 10.
Why do we want it greater than 10?
Because our rule of thumb says that if n times p is greater than or equal to 10, and n times 1 minus p is greater than or equal to 10, then a normal approximation can be assumed to be reasonable.
Okay.
We're just checking to make sure that we can assume it's normal first.
Yes, sir.
If it doesn't meet those two requirements, we can't move on with normality. On the wrong way. There we are. So 1 minus 0.07 is 0.93. What's 200 times 0.93?
186.
186. Is that greater than or equal to 10? Yes. So can we assume normality?
Yes.
Yes. We can. So now that we know we can assume normality, we need to figure out what's our mean and standard deviation going to be. That's where our rules 1 and 2 come in. If you remember rule 1, we said that the mean is equal to our population proportion. So the mean is equal to P. What is P?
.7.
0.07. Good. And then our standard deviation, P hat, is the square root of P times 1 minus P over N. I'm about to do 0.07 times 0.93 over, let's see, what's my N? 300. So what does that give us to 3 decimal places? 0.018. Oh, and AP, before I forget, I told last period, but I haven't told y'all yet. So at the end of the 9 weeks on Friday, I'm going to drop y'all's lowest test grade. Yes.
You want to go for test grade, right?
So on Friday, before they pull grades, I'm going to your lowest test grade.
Well, that's Mr. Schultz.
Y'all have only had 2 tests. I can't do that.
What about homework, though? What about homework?
Oh, so I can't do that on y'all's because the college doesn't do that. But here's what I will say. At least this 9 weeks I can't do that. Next 9 weeks, I'm glad you asked me that because I need to let y'all know this. So from admin, they came down and told us that for dual credit, your grades can't, and Skyward can't follow the syllabus. They have to follow district policy, which means homework has to be 30%, tests have to be 70%.
Okay.
Which, for the second 9 weeks, will actually help y'all out, because on the AC syllabus, homework's only 16%. The homework counts more. Flip side of that though is when you look in Skyward and you look in Blackboard starting Monday, the grades will look different.
In a good way.
It just depends on how you do on test versus homework.
So you're saying, so wait, if they see it as a 16%, wouldn't that mean that it counts more here?
Yes, homework counts more here, yes.
Alright.
Does that make sense?
Yes, sir.
So if y'all start seeing differences in Skyward versus Blackboard, that's what's going on.
I remember that from history last year, because I had a grade in Docret in college, or in AC, and I had a different grade in Skyward.
Yep. I was told last year I could keep them the same, and then they came and just told me today, no, you can't do that. And now you tell me. After I've done like this for 3/4 of a year now. Okay, anyways, back to this example. So we found our mean and our standard deviation. We still haven't answered the question though. We have to say if this result indicates basically a better treatment. And what we're wanting to find is the probability that p hat is less than 0.03. At this point, since we assume normality though, we can just turn these into z-scores. And that's what we'll do. We're going to turn them into z-scores. Z is less than 0.03 minus 0.07 over 0.018. Okay, so what do we get for the z-score? Negative 2.22. Now I look that up in my table, and what do I get for my probability? Point 032, that's right.
I guess it's safe to say that they're correct about the less than 7.
Yeah, I think they're safe to say that too. So this small probability tells us that it's unlikely that a sample proportion of 0.03 or smaller would be observed if the screening procedure was ineffective. Which means if it's not ineffective, it has to be effective. So the new screening procedure appears to yield a smaller hepatitis rate, which is a good thing. Yeah. Okay. Questions on that one?
Oh, what is this Z?
So that's just where they calculated the z-score.
Do you have to do that?
Well, like this is where, so what they did here, this right here is that right there. I just wrote on top of the slide. I didn't create a new slide like I've done in the past. I'm just writing on top of what they had. And they made a separate statement to say, oh, here's what Z is. Now let's plug it in. I just have us do one long equation. I find that's easier just to put it in the equation as you do it, because then you can follow the logic rather than write something. Oh, let me go over here and do some scratch work. Put it back in. Oh, let me go do more scratch work. Put it back in. Keep the flow. Okay, next example. So if the true proportion of defectives produced by a certain manufacturing process 0.08 and a sample of 400 is chosen, what's the probability that the proportion of defectives in the sample is greater than 0.10? So first thing we have to do is determine, can this be assumed normal? That's our first step. So let's see here. We have to do n times p. What would our n be equal to here? 400. What's our p? Go ahead, Raleigh.
What is the n times p? Because I remember last time it was mu or something. What is it this time? For now?
What's n times p? Right now we're just checking. It's not really, it doesn't have an official letter. So for the binomial distribution, you're right, it is mu. But right now it's just a method of checking. There's not like an assigned letter.
I was just checking like if it was like different. Or in TV, finally.
Yes. Okay, where did my pen go? Oh, there it is. Okay, so now I have to do n times p. So MP is 400 times 0.08. So what would that get us? 32. Are we greater than 10? Yes. So 4, we're good. Now we have to do n times 1 minus p. 400 times 0.92. What would that get us? 368. Are we greater than 10? Yes. So can we assume normality here? Yes, we can. Okay, so next since we can assume normality, we need to find mu and sigma. So mu of p hat, what should that equal? That should be our population proportion, which is 0.08. Then we need to get sigma of p hat. That's where we do that big old square root. 0.08 times 0.92 divided by, what's our n? 400. So what do we get for sigma here? What's that?
0.0.
Now let's use more decimal places so we're a little bit more approximate. 1, 3, 8, 5, 6, 5. Okay, so we've got our mean, we've got our standard deviation. It's also right up here.
So far it works if it's resolvable using normal.
Oh, that one? That part. Okay. Okay. So again, there's our mean and standard deviation that we just calculated. The question asks us to find the probability that the proportion is greater than 0.10. The probability that p hat is greater than 0.1. Since we said that we can use the normal approximation, let's find our z-score. This is the probability that z is greater than, let's see, I gotta do 10 minus 0.08 divided by 0.13565. So if I calculate this, what would I get? Probability that z is greater than, yep, 1.47. Now, does my table give me the probability that z is greater than something? No. It gives me less than. What do I have to do to this value? 1 minus, that's right. So if I look up that value in my Z table, what should I find? .9292, that's right. And when we do that subtraction for our probability, what do I get? 0708. Okay, now, they don't ask us this, but just to kind of make sure dual credit, I'll stay on y'all's toes about this. Would this be considered unusual?
No,
No, why not?
at least not less than 105.
Perfect. Okay, questions on this one? Okay. Last example, before we have to go into a little dual credit add-on. Okay, so suppose that 3% of people connected by phone are receptive to certain sales pitches, and they buy your product. If your sales staff contacts 2,000 people, what's the probability that more than 100 will purchase your product? What do we have to check for first? Normality. What would my N be in this case? 2,000. What's my P? 0.03. So N times P is 2,000 times 0.03, which is what? 60. Does that value check out to be greater than 10? Yep. Now,
if it doesn't, if it's not greater than 10, do we just like stop the problem or what?
you would have to, you couldn't do normality, so in our case, we would have to say it's not normal and then try to find what distribution it actually is. So we're going to talk about that when we get to y'all's little extension in a second.
Okay.
But, so, almost hate saying this, but for dual credit, the extension is really what I'm concerned with on y'all. I'm going to actually tonight have to create a little video for y'all so we can work examples that run this. This is close to what we're doing now, but not exactly. So I'm going to put a video in Blackboard tonight to help y'all out. May or may not be a homework problem. Okay. So N times 1 minus P, 2,000 times 0.97 is what? Yep. Does that check out to be bigger than 10? So are we normal? We are. Let's find our mean now. So what should our mean be equal to then? 0.03. And our standard deviation? We're going to have to do that whole 0.03 times 0.97 over 2,000. I'm going to give this one to y'all because I want a bunch of decimal places here to be accurate. 0.003814446.
2 zeros.
Okay, so now I have to use this to find the probability. Probability is that p hat is greater than. Now I can't say 100 here because I need a proportion. I'm gonna have to say 100 over 2,000. So what is 100 divided by 2,000? Point 0.05. And now I just use my normal approximation here. The probability that z is greater than 0.05 minus 0.03 divided by our lovely standard deviation. What do we get for our z-score? That's right, 5.24. Now, does our table give us that as greater than? No, so I need to do 1 minus the probability that z is less than 5.24.
Oh, good.
Yeah, that's a little big for our table, right?
Mm.
What would the probability be of that then? 1.
Wow.
Because if we look at the biggest point in our table,
It's like 0.999.
no. And then we're going even bigger, so this is going to be 0.99999999999. Yeah. So we'll just say 1. Well, what's 1 minus 1? 0. That's our probability. So,
Even at 0.9, like 0.29. You rounded to 29, so it would be 1, right? It's supposed to go up.
yeah. Okay, now here's what I'm going to do. I need to talk about this binomials handout. So I'm going to give y'all the answer to that last question. Eventually, at some point, I want y'all to just fill your notes out and work it to make sure it's a way to check to make sure you understand it. Does that sound fair enough? Okay, so on this last one, the very last one, you should get your probability that p hat is greater than, I'm sorry, not greater than, p hat is less than 0.025 equals 0.0951. That's what you should get. So, AP, you can do it now if you want. I mean, we're done with the notes. We're going to go over this binomial deal for full credit right quick. Yes. Ooh, dual credit. I forgot to tell you something on the homework due tomorrow. It's something good, I promise.
Okay.
One more question.
I know you still got to do it, but there is a problem you don't have to do. Okay, so if you look on the last page of the one due tomorrow, this isn't it. This is a handout. If you look on the last page of the one due tomorrow, you'll see two graphs that are kind of spaced out. Let's say A and B. Well, the answer is either C or D, which I can't see. So cross that one out. I'm not putting it on there.
So the entire question 8?
Well, not just that part of question 8. You're going to have to do the calculations, but you're not going to have to graph it. I don't think that's fair to surprise y'all on Blackboard with that 2 extra answer choices. On question 8, you see how there's 2 graphs that are kind of spread out? Mark that part out. So just mark the graphs out, basically.
Do we need our pencils anymore today, or just?
It's up to you. You want to take notes? You can. If not, I'm just going to be able to read off this. I can't write anything on it. So. Okay, so real quick. Like I said, I'm going to do a separate video tonight to go a little bit more in depth on this. But for the binomial distribution, these go with the assignment I gave you today. So keep these together. One difference is that we don't want NP to be greater than 10. We only need it to be greater than 5. If it's greater than 5, you can use normal for binomial. Same thing with n times 1 minus p. Greater than 5, you're good. For the mean and standard deviation, notice that those are your mean and standard deviation for the binomial distribution. That NP that you were mentioning, Riley, that's the mean and standard that's the mean that you would use for y'all's homework. Then sigma is the square root of n times 1 minus p. Okay. Continuity correction. There is an error on here that y'all need to correct before I forget. So that bottom example where it says the probability of 3 to 6 successes, not including 3 and 6, where they say 2 is less than or equal to r, that should be a 4 is less than or equal to r. Let me explain why. So if I have to be between 3 and 6, let's say I'm flipping a coin and I want to be between 3 and 6, but I can't include those. What's the next one above 3 I can't include? If I'm flipping a coin. So I can't flip it 3 times, I have to flip it 4. So where it says that's equal to 2, between 2 and 5, that should be between 4 and 5. So on that last bullet point, those should be 4s, not 2s. But on the continuity correction, what that is saying is that you must adjust by a half for continuity. At this point, I'll explain this all in the video that I'm going to put on Blackboard. So tonight or tomorrow, check Blackboard and look for a binomials video. That sound good?
Yes, sir.
I think since I didn't even get to talk about it much, I think I'm going to do a homework problem video. How's that sound?
Sounds good to me.
Sounds like you need a nap.
Mr. Schultz.
Yes.
Have a good day.
See.